Monosaccharide reactions. The first important reaction is oxidation, and this reaction we use it to identify monosaccharides in there and identify the property of the monosaccharide, which is reducing sugar. So what is a reducing sugar? A reducing sugar is simply a carbohydrate. It can be a monosaccharide or it can be a disaccharide, it depends. But that carbohydrate has to have a functional group that can be oxidized in there. Now, the oxidizing agent that we use is a Benedict solution. And this is a blue solution which is made up of copper hydroxide. Okay, so what we do is we put our monosaccharide, and this is called a test for reducing sugars, if our monosaccharide is a reducing sugar or not. Meaning, does it have functional groups that can be reduced? Okay, we put our monosaccharide, we add some Benedict solution to it, and if our monosaccharide is a reducing sugar, then in this case, we will form an orange-red precipitate, and the compound is going to be oxidized. Now, these are examples in there. We have an example of an aldose and the ketose. All of those, they do have, for example, aldoses, they have aldehydes in there. We know that aldehydes can be oxidized into a carboxylic acid, right? So all of these hydrogens in there will turn into an OH. So this is going to be a positive test. So all monosaccharides that have an aldehyde functional group, these are considered to be a reducing sugar. Same idea for the ones that have a ketone functional group in there. Because for ketones, I do have an alcohol in here, and the alcohol can be oxidized. And the oxidation of that alcohol is going to be into a carboxylic acid. So let's go ahead and have an example in there. So we have here an example of an aldohexose. This is an aldehyde. We reacted with a Benedict solution. This is a copper hydroxide solution which is blue. So by definition, aldehydes are oxidized into a carboxylic acid. This is an old reaction that we talked about, where if we go ahead and put it this way, so you have your carbon double bond O and the hydrogen. So that hydrogen over here will turn into a carboxylic acid. So you will end up having your carbon double bond O, and you're going to end up having your OH. So that hydrogen will be oxidized into an OH, and you will change the aldehyde functional group into a carboxylic acid functional group, and you're going to form an orange-red precipitate. This is called a positive test that you are starting with a reducing sugar in there. Okay? There are different colors that you might form in there depending on the amount of the reducing sugar that you have. So let's say, for example, if you start with a monosaccharide and you get a blue solution. Now we know that the Benedict solution is already blue. So if your color remains blue, this means that you don't have a reducing sugar in there. There is no reaction. On the other hand, if you got a green and a yellow precipitate, this means that you have traces of reducing sugar. If you have an orange-red precipitate, then you're going to have a moderate reducing sugar. To get a good amount of copper oxide, which is a brick red precipitate, this means that I have a large amount of reducing sugar. So these are the 4 different colors in there and 4 different color variations that tell you exactly what is the quantity of reducing sugar that you are starting with. Now for ketohexoses, like for example fructoses, these in presence of a basic medium, because you are adding the copper hydroxide Benedict solution. So this is a basic medium. So the carbonyl of the ketone, this is what happens. The carbonyl of the ketone, it changes into into an OH and they're into an alcohol. So you're going to end up having an alcohol and the hydrogen. So that was once the carbonyl of the ketone, and it turned into a COH in there. It's just rearranges, and the alcohol changes into an aldehyde. So basically, the ketone rearranges into an aldehyde in there. This is what it does. And then once you add the Benedict solution in there, so remember you do have a basic medium. So the basic medium is going to allow the ketone to rearrange into an aldehyde. So the fructose will turn into a glucose in this case. And then in presence of the copper hydroxide Benedict solution, then this hydrogen will get oxidized further, and you're going to end up getting a carboxylic acid in this case. So that is going to be the OH, plus of course your precipitate, your orange red brick color precipitate in there that tells you that this is a positive test. So monosaccharides, all monosaccharides, these are the aldoses and the ketoses. Both of them, they are considered to be a reducing sugar because they do form a copper oxide precipitate in there, and they can oxidize the aldehyde functional group into a carboxylic acid. This is another example of monosaccharide, aldose. Galactose is an aldose. So here what's happening is that the aldehyde is being oxidized into a carboxylic acid in this case. You are responsible to know this reaction here. I'm not going to ask you about the ketone and its rearrangement in here, but you have to know that with these reactions we are turning the aldehyde into a carboxylic acid. Plus, of course, you will have your copper oxide precipitate in there, which is an orange-red precipitate. Another reaction of the monosaccharide is the reaction of the phosphoric acid with the OH group of the monosaccharide. Those two are going to react with each other, and you're going to get the phosphate ester. So the CH2 will lose the OH, and the phosphoric acid will lose all of its hydrogens in there. And you're going to form a bond between the carbon and the oxygen of the phosphoric acid. So actually you're going to form a kind of a phosphate ester in this case. So your product is going to be a CH2 in there, and then the rest of the phosphate molecule without the hydrogens. So you're going to have the O. This is going to be the double bond O. It looks like a phosphate ester, and that is going to be an O. All of these oxygens, they lost their hydrogens, so that is going to be a negative charge. Pretty much this is it. So you're going to end up getting your phosphate ester. So when I want to name this is going to be named based on the monosaccharide that it started from. So that is going to be an alpha glucose. So the name is going to be an alpha glucose. Okay, and it's going to be on carbon number 6 because the reaction is on carbon number 6 in there. This is the reaction. So it's going to be 1, 2, 3, 4, 5, and 6. So that is going to be carbon number 6. So you have to specify where is your phosphate is. And your phosphate is on carbon number 6. So that is going to be phosphate. You are responsible to name this structure. This is an example of a pyranose whenever it reacts with H3PO4. Same idea when the furanose reacts with H3PO4. We're going to do the same thing. So the OH of the fructose in this case it's going to react with the hydrogen of the phosphoric acid, and also the phosphoric acid will lose all of its hydrogens in there. And your product is going to be the phosphate ester. So it's going to be the CH2, and then you have the, let's draw it in this color, you have the oxygen, and then the phosphate. Let me draw it on the other side so that I have enough room in there. So I have my oxygen here, and then my double bond O. This is why I call it an ester in this case, and this is a negative charge, and that is going to be my product in this case. If I want to go ahead and number, then that is going to be carbon number 1. Remember, when we number from the number the fructose, we start numbering from here to be carbon number 1, 2, 3, 4, 5, and that is going to be, this is oxygen 6, and this also can be carbon number 6 as well. So when I want to name that, it's going to be 1, 2, 3, 4, this is 5, and that is 6. This is oxygen 6 as well. So the name is going to be a beta fructose. It's going to be on carbon number 6. I have my phosphate, and you are responsible to name those. The third reaction is the reaction of cyclic monosaccharides with alcohols to form acetals and ketols. In general, we already know that if we have a hemiacetal, okay, and this is a hemiacetal in here, and since you have a hydrogen there, so this is why we call it a hemiacetal. And you react that with an alcohol, okay, in presence of an acid, then the OH is going to change into an OR prime in that case, and you are going to form an acetal. We are going to follow that same general reaction over here. So we have a hemiacetal. We are starting with a monosaccharide. This is a pyranose cycle of alpha D glucose, and that is a hemiacetal. See, when I want to check if my monosaccharide, cyclic monosaccharide, is an acetal or a hemiacetal, all I need to look for is at that anomeric carbon over here. So this is my anomeric carbon. So this carbon over here is my anomeric carbon, and this carbon is going to determine if I have an acetal or a hemiacetal. So if you look at this carbon here and you see that this is a carbon that has an OH and then OR. Do you see? This is a carbon with an OH and an OR. So an OH here and OR there. Then I would know that this is going to be a hemiacetal. That is going to be a hemiacetal carbon in this case. So for hemiacetals, they are going to react with another mole of the alcohol, and that OH is going to turn into an OCH3. Okay, so the OCH3 that you are going to add over here, since it is on the anomeric carbon, you have two options. Either the OCH3 is going to be on the alpha, or the OCH3 is going to be on the beta. And whenever I want to name that, so what I formed over here is what we call a glycosidic linkage, because we formed an acetal. What we formed here is a carbon that is connected to an OR and another OR. So this bond here is called a glycosidic linkage. Let's put it over here. So this bond is called a glycosidic linkage. Okay, same thing for this bond there. It's called a glycosidic linkage. So whenever I want to name this structure over here, then I'm going to start by naming the R that is connected to the oxygen first. So the name here is going to be a methyl. And then I know that the OCH3 is pointed down. So that is going to be my alpha anomer. So that is going to be alpha. This is derived from D glucose, right? So the name is going to be a D. And then that is a cycle of 6-membered rings. So that is going to be a pyranose. It is derived from D-glucose, so that is going to be a D-glyco. And then since the cycle here is a pyranose, it's going to be a pyranoside. So that is going to be a glyco pyranoside. Okay, same thing over there. That is going to be a methyl. It's a beta. It's derived from a D-glucose, which is a glyco. In that case, this is a pyranose. It has a glycosidic linkage, so it's going to be a, let's continue over here, a pyranoside. Glycosides are always cyclic structures, and they do not exist in an open form because they do have a hydrogen in there, a CO and another CO. These are acetals, and these cannot be oxidized further, so we cannot have them as reducing sugars. They are never reducing sugars in there. Okay, so these with a Benedict solution will give me a negative test, meaning that the solution will remain blue in color.